aller? Le micro? Comment?
Un micro ou deux micros?
Bah, juste un micro pour l'instant.
Il y en a un là.
Il est où là?
Il y en a un autre si quelqu'un. Non, prenez celui-là, c'est parfait.
Ok. Bon. So let's get started this presentation. Hi everyone. So my name is Mohand ADJEMOUT and I'm a Research and Development Manager at LATTY International Lab. And today I have a pleasure to present you a couple of studies aimed on the topic of untitled Post Fukushima saline solutions with two saline solutions. We have a gasket solution, O-ring solution, and packing solution for valves. So the outline of this presentation is divided on two subtopics. So the first topic concerns qualification of low friction valves, packing solution for nuclear application, while the second study concerns qualification of static and dynamic O-ring for mechanical seal, which is also dedicated and concerns nuclear application. So let's start with the first study. So here we have an example of valve. So a main structure of a valve is composed with an actuator which drive the steam and the positioner which give us the desired position of the steam, and we have a body where we have the pressure to be confined and to be sealed. And in the valve, generally you find a solution or saline solution to avoid fluid escaping from the confined fluid to the atmosphere. So here we are concerned with a packing solution, so saline solution with packing. And a packing is generally composed with ring stacked on the stuffing box and compressed by means of gland follower due to the force and effort generated by the tightening system. So basic composition of packing are shown here, and the ultimate goal with such a saline solution is to prevent fluid escaping from a high pressure confined fluid to the atmosphere environment. And with saline packing or with packing solution, this is seated by mean or due to the gland force applied by the gland follower on the ring stacking, which then is converted to radial force and an axial force, which is transmitted and repeated through the stuffing box. Okay, so when the steam is actuated, so we create a relative movement between the steam and the packing or the saline packing, and this will generate a friction force, a dynamic friction force between the two moving parts, which give us a general situation which consists of, by increasing the gland force, we tend to eliminate the leakage, but in the same time we increase the friction coefficient. While the desired and the ultimate goal when designing a packing solution is to get the solution where the friction coefficient is the lowest and the leakage is eliminated. So the aim when designing a packing is to get this both tendencies, is to say eliminate leakage and fluid escaping, and at the same time reduce as minimum possible the friction coefficient. Okay, so the friction coefficient of packing is one of the most crucial parameters which directly influence the maneuverability of a steam on a valve, and this parameter was identified by EDF as one of the axes of improvement in order to avoid either change of the actuator's strength and power, and to not deal with heavy and a lot of modification on the valves. Okay, so in this context, Lecce International developed two kind of solution with different material dealing with this issue. Is to say we get a low friction coefficient, which then allow us to not deal with a lot of and tough modification of the valves. Okay, so these two developed solution needed to be qualified. So in this context, a partnership was launched by EDF in order to qualify these two products, and this qualification have been realized and carried out within the SETIM laboratory. Okay. So now we will see together the saline solution. We have a first solution, which is a PTFE-based solution, and it's composed with saline ring and end rings in the top and the bottom. The saline rings are composed is a combination between the Latiflon 3265 FR and the Latigraph 8944 BS. The second solution is a graphite-based solution. So this solution is a combination between the Latigraph 9110, and we kept the same solution for the end rings, which is the Latigraph 8944 BS. Okay, to see in detail this two product, the Latiflon 3265 FR is a plated impregnated carbon yarn in the middle of the ring, in the core, in the heart of the ring, and covered with PTFE braided yarn treated with a special lubricant in order to reduce friction coefficient. All this material have been treated with corrosion inhibitor in order to protect and avoid any corrosion reaction, chemical corrosion between the steam and the saline solution. While for the Latigraph 8944 BS, it's made of graphite yarn Econel reinforced and coated with graphite and also a kind of lubricant or an anti-friction mixture. Okay. To show you a braiding process here, I got a movie. I will try to start it for a few seconds in order to give you the braiding process. Okay, for the second solution, which is a graphite-based solution, we have the Latigraph 9110, which is made of high purity expanded graphite impregnated with also the same special lubricant and pre-compressed and treated by a corrosion inhibitor. While for the end ring, we kept the same solution with the Latigraph 8944 BS. So the pre-compression can be made with different manner. Here we got semi-automatic manner to show you how the expanded graphite lubricator impregnated is manufactured. Here we have an example of small rings. Okay, so to qualify these two products, a campaign or testing campaign have been carried out and built up in collaboration with EDF and SETIM, and it consists of two protocols. We have the first protocol, which aims and the purpose of the first protocol is to qualify or to test under normal condition, and it consists of corrosion test at high temperature and ambient temperature, and we have mechanical cycling in order to test against the mechanical testing, the mechanical behavior, the packings. The second test concern assessment and analyzing the packing against accidental condition, which is much more severe and much more needs a lot of care to take with the saline solution. So the tests start with tightening test with air, followed with cycling test at least with 1,500 occurrence. After that, the test cell have been dismantled, and put it in a kind of reactor in order to be exposed to gamma ray. So the radiation exposition consists of going by step, is to say that we make a first step of irradiation, absorption, and after that we made functional test followed with tightening test. If the result of this test or meet the requirement, we go to the next irradiation step, and we do so on until we get a maximum absorbed dose of 4 megagray at the end, in which corresponds to the absorbed dose. Okay. After that, the test cell or the packing are dismantled and analyzed. All these tests have been carried out within the SETIM laboratory with their own facilities. Okay, here we have the result of corrosion test. For both corrosion tests at ambient temperature and high temperature, no corrosion occurrence was observed, and this is probably due to the corrosion inhibitor that we have used during the manufacturing, which protect the steam from corrosion attacks, and more especially galvanic corrosion. For the cycling test with the graphite solution, we have here an example of cycling test where we assessed the leakage and the friction coefficient. Okay. For a functional test or for a nominal condition, the maximum leakage allowed is about 5 millimeters per hour. And during all the tests, no leakage was observed. Okay. In terms of friction, first it has to be noted that the friction coefficient given here is a modified friction coefficient and not correspond to real friction coefficient. Okay. And the results show that with this new generation, the friction coefficient was reduced compared to a previous solution with about 30% of gain. And this was firstly seen during the beginning of the test. After that, the friction coefficient increased gradually as function of the cycling, but did not exceed the maximum limit allowed, which equal value 12. Okay. After that, another test without pressure was done and was realized, and we found that the friction coefficient was stable in range between 10 and 12. This for the graphite solution. For the PTFE solution, the same is to say for the leakage, no leakage and no extra leakage was observed. In terms of friction coefficient, here we observed a very low friction coefficient, which has the tendency to decrease as function the cycling is going on until we go down the value of 1. After that, we made test without pressure, and the results show that the friction coefficient was stable averagely at value of 2. So this for nominal operating condition. For irradiating test, we found first in terms of leakage, no leakage or no exceeds in terms of leakage was observed, and the criterion for both condition during cycling at normal condition and after 4 megagray absorbed dose, the leakage was increased, but no leakage was observed. And the most important result is after the radiation exposition, the friction coefficient was assessed, and the interesting result, it was found that the friction coefficient remained stable as the same we found before doing the irradiation tests, which is a quite interesting results. The same was done with the PTFE solution, and the same conclusion can be drive it out is to say that the friction coefficient before and after irradiation remain the same, and most importantly is remained constant. So when we finish the test, the packing are dismantled and analyzed, and no excessive damage or abnormal degradation was observed on both solution, and except some extrusion and some abrasive particle, which is quite logical due to the nature of the graphite in the PTFE, and no abnormal damage or excessive even after this this level of radiation absorbed dose. So to conclude for this first presentation, in order to qualify a new product given or new saline solution with low friction coefficient, a partnership have been launched by EDF. LATTY bring out two solutions giving or reducing friction coefficient, and allow us to get two solutions giving a reduction on friction coefficient about 30% up to 70%, depending on the nature of the solution, if it's PTFE or if it's graphite. And the most important with this qualification is it's resistant to high absorbed dose, which here on assessed here up to 4 megagree. And after this testing and this qualification, the packing have been approved for accidental condition, for regular valves and or online valves for different categories, and most importantly for operating condition with irradiation and accidental conditions. So now we move to the second presentation, which also concerned operating condition at irradiated environment. But here we are concerned with elastomer, which is a kind of organic material and more sensitive to the irradiation. So here we have a cross-section of mechanical seal, and in the mechanical seal, O-rings are widely used due to their elasticity and their useness. So in a mechanical seal, we can find two configuration of O-rings: static configuration and dynamic or semi-dynamic configuration. And in the context of developing ultimate safety PAMs, there was a need to develop new performant mechanical seal, and LATTY International proposed to qualify mechanical seal with O-ring solution. And in order to do so, we have to qualify the elastomer, which is the most sensitive in the mechanical seal. Okay? So to do this, LATTY International invested and carried out a study to develop new elastomer and qualify them. So we have been collaborated with EDF and also with the CETIM laboratory, which was chosen as the testing partner. And test procedure have been built up with respect to the EDF requirement, and in order to increase our chance and our probability to get new solution and reliable solution, different material with different hardness, with different formulation of elastomer have been developed and manufactured and assessed. The strategy of testing consists of successive mechanical and thermal and irradiation agent with functional or hydrostatic test after each level of agent, in order to assess or to assess and verify and check the salability of the product. Okay, so to see in detail the qualification procedure, so we made mechanical agent cycling during 500 hours, followed with thermal agent during 240 hours, and followed with another kind of agent, which is named accidental agent, and at the end we finished the test with irradiation, with a maximum absorbed dose of 1,700 kilograms. Here we have the testing still given in detail. So we fit the two identical O-rings in a test cell, which allow to fill it with water. And the shaft can slide with a magnitude situated between minus 0.3 and plus 0.3 with a frequency of 5 Hertz. Here we have the elastomer, which was developed and qualified during this study, which is a special PDM material. And now we'll see together the result. So here we have the result of the mechanical agent, the recorded parameter, and friction test in order to assess the level of friction created between the sliding shaft and the O-rings. After this, hydrostatic tests have been made at a pressure of 14 bars during 15 minutes, and the results showed no leakage was observed, or the leakage was nil. After that, we moved to the thermal agent, and we made hydrostatic test with the same manner, and no leakage was observed. We did so with accidental thermal agent. Here we have the recorded parameter and the hydrostatic test, and here also no leakage was observed. After all this mechanical and thermal agent, we made the irradiation test, and after that the mechanical or the testing cell have been assessed in terms of friction reaction, and the result was compared to the one observed before the test. So here we have an O-ring with absorbed dose of 1,700 compared to the new one. Let's say that compared to the new one. And the results showed no deviation was observed between a new one and aged one. And most important result is the signature or the behavior of coring kept sliding without wrapping, which is a quite important result, because with this manner we eliminate a kind of tear and shear stress on the O-ring, and we increase its lifetime. So here we maintained a good or a desired behavior. And after that we made also hydrostatic test, and during this test we increased the pressure up to 25 bars instead of 14 bars, and the result here also showed no leakage. Okay, after all the overall test, we dismantled the samples and we assessed them and we analyzed them. So we measured the mass before and after, and no deviation was observed. And in terms of observation, a cross-section of the O-ring gives a good aspect, and the most important, there is no extrusion observed on the O-rings. Okay, and this is probably due to the sliding without wrapping. Okay, this result was confirmed by the measure of the hardness before and after the test in different sides of the O-ring, and here we can see that the level of the hardness measured after the test remained at the same level and the same uncertainty of a new O-rings, which is a quite interesting and a good results. So, to conclude this presentation or this second study is to say that an experimental qualification have been carried out and presented here. Through this qualification, we approved elastomer for high gamma ray absorbed dose, and the O-ring was qualified for static and dynamic configuration or application, And the most another important thing to be pointed out is that the elastomer formulation meets the chemical specification of the PMUC regulation, which limits the maximum content of the sulfur and the halogen on the product. So is to say that the O-ring have been homologated PMUC product. Okay, so that's all for me, and thank you for your attending this presentation. And don't hesitate if you have a question. And also, I invite you to meet us in our booth K62 with our team, and it's our pleasure to answer to your question and discuss further on these two topics. Thank you.